Hi everyone, my name is ECG. I'm lecturer from Faculty of Electrical and Electronic Engineering. So in this video, we are going to solve for question number 2. Okay, so the first question is define Biot-Savart's law. Okay, so to be precise, so in this question, actually we just need to solve for this one, okay, which is to define the Biot-Savart's law. Okay, so these definitions about the Biot-Savart's law, you can refer to our notes. Okay, so this is the sentences from the notes. Okay, so Biot-Savart's law tell us that the differential magnetic field intensity, which is the DH, okay, produced at one position P, okay, by differential current element IDL at a point P is proportional to product of IDL and the sine of the angle between the element and the line joining the point P. Okay, so you can write in this way. So the DH, okay, is proportional, okay, is proportional to the proportional to the product of IDL, okay, and the sine of the angle, okay, so just write down in this way, sine of the angle between the element and the line joining the element, and it is inverse proportional to the square of the distance. Okay, so you can just write out this one as the formulas to represent the Biot-Savart's law. So now let's look at question B. Okay, so you have a semi-infinite conductor, and this conductor is bent into L shape, okay, running along the y-axis from these positions, okay, to the origin and continue along the positive z-axis. Okay, so you should imagine how these conductors oriented. Okay, so z, y, x, so it is coming from here 6, right? And then when it stops at the origin, it will continue in the positive z directions. Okay, so this is the conductor. So this conductor is carrying a steady current, so the current is 3 ampere, and at point P, okay, so point P is your observation point. Analyze how each segment of the conductor contribute to the magnetic field and determine the net magnetic field intensity at that point. Okay, so we can break this conductor into 2 sections. Okay, so first section is from 0, 6, 0 until 0, 0, 0. Okay, and the second section is from 0, 0, 0 until infinity. Okay, because this is a semi-infinite line. Okay, so this one is extend to infinity. So you have to find the magnetic field. Okay, so the total magnetic field will be the magnetic field contributed by element 1, which is a finite line. Okay, and element 2, which is a semi-infinite line. Alright, so now let's look at the steps to find the H1, okay, which is from the segment number 1. Okay, so the observation point is -3, 6, and 0. So we need to locate this point first. So -3, okay, -3 might be here, and 6, okay, 6 is here, right? So if you extend both lines, so and 0, okay, so this one is your point P. Okay, the point that you need to find the magnetic field. Okay, the point that you need to find the magnetic field. Okay, so this is a finite line. So for finite line, you have to use suitable equations. That is I over 4 pi r, right? And then cos alpha 2 minus cos alpha 1 and phi. Okay, and phi, yeah. Okay, so in this case, we need to identify what is the I. So according to the questions, the I is 3 ampere, right? So you can write the 3 ampere. And you need to determine what is the R, what is the alpha 2, and what is the alpha 1. So to determine the R, first thing you have to find what is point T. Okay, so point T would be along the axis that has your line, which is along the axis y. So for axis y, all the x value is 0 and all the z value is also 0. Okay, so for the y value, you will follow the y value of the observation point, which is 6. Okay, so this is how we determine the point T. So 0, 6, 0 means that it is this point. This is your point T. Okay, so you have to find the R. Okay, so it will be -3, 6, 0 minus 0, 6, 0. So you have -3, 0, and 0. This is your distance vectors. And for the distance, it will be 3. And for the unit vector r, it will be -x. Okay, -x. Okay, -x. Okay, so you have got your r, which is 3. Now we have to determine the alpha 2 and alpha 1. So to determine the alpha 2 and alpha 1, you have to redraw again, okay, your current filaments. Okay, so here would be your y-axis. Okay, that has your current filaments, right? Okay, your y-axis. Okay, so here might be I will choose the x-axis. I will choose the x-axis over here. And I will label it as -x. Okay, because for the point P, okay, the position is 3. So it will be over here 3. Okay, -3. Okay, so if you plot the observation point in this diagram, it will be here, right? Because the y and x, no, it should be here. -3 and 6. -3 and 6 is here. Okay, -3 and 6 is here. So this is the point P. Okay, so this position is 6 and this is 0. Okay, so your next step is to join them. Okay, your next step is to join them. Okay, and here will be point A and here will be point B. Okay, so alpha 2 will be over here. Right, we'll take the inner radius. And for the alpha 1, it will be stick with the point A and we will take the outer angle. Okay, so now we need to find what is the alpha 2. So over here we know the distance is 3 and this is 6. Okay, so the alpha 2, so for alpha 2, okay, it is 90 degrees, right? Because it is a straight line. And for the alpha 1, okay, we are going to use this formula. Tangent 180 minus alpha 1 is equals to opposite over adjacent. Opposite over adjacent. Okay, so let's calculate this. Tangent. Okay, so alright, wait, I'm setting my angle in radian, so I want to set it to degree. Okay, so this is alpha 1 is equals to 180 minus 26 something, so it will be 153.43, okay, degree. Okay, so now we are going to replace it inside the formula. So we have H equals to 3 ampere over 4 pi r. R is 3. Okay, and then we have cos alpha 2. Okay, 90 minus cos 153.43. Okay, and for the phi, okay, for the phi, it is dl cross with the r. Okay, so now current is flowing in this direction, right? Flowing in this direction, so negative y. So it's negative y cross with the negative x. Okay, so this we get it here. Okay, so negative negative we cancel, so yx we get negative z. Okay, we get negative z, and then let's calculate this one. So we have cos 90 minus cos 153.43. Okay, and then we divide with 4 pi. Okay, so the answer is 0.0711. Okay, and the unit is ampere per meter. Okay, in the negative z directions. Okay, so this is the first magnetic field. So for the second magnetic field, okay, so this is the diagram. So this is a semi-infinite line. Okay, so for semi-infinite line, I would prefer you to use the same formula just like the finite line, because you can approximate the angle for the alpha 1 and also alpha 2. Okay, so this is the formula that we have to use. I over 4 pi r, okay, cos alpha 2 minus cos alpha 1. Okay, and then we have the phi. Okay, so now we have to determine where is the point T. Okay, so point T would be along the axis that has your current. So this time, okay, it is axis Z. Okay, so for the X and Y, they are all 0. Okay, and for the Z, you will refer to the Z of the observation point. So it is 0. So for your R, it will be equals to negative 3, 6, 0, minus 0, 0, 0. Okay, so you have negative 3, 6, and 0. And then for the distance, okay, it will be 9 plus 36. So you have square root 45. Okay, square root 45. And your unit vector r, it is negative 3 over square root 45 x plus 6 over square root 45 y. Okay, so this is your r. Right, so now we have to determine the alpha and alpha 2 and also alpha 1. So we need to redraw again, okay, our diagram. So here I will refer to Z. Okay, so over here I will choose versus Y. Okay, I will choose versus Y. So the observation point is 60. Okay, 60 is here. Right, 60. Okay, so my current filaments, my conductor is from the origin until infinity here. Okay, so if I join the line, okay, here will be point A and here will be point B. So obviously over here your alpha 1 is equals to 90 degrees. Okay, and this is your alpha 2. Okay, so when your B is extend to infinity, okay, your alpha 2 will become smaller and smaller, and we will say that it is approximated to 0 degree. Okay, 0 degree, yeah. Okay, so now we can plug in the formula, we can plug in the value into the formula, that is 3 over 4 pi square root 45. So alpha 2 is cos 0 minus cos alpha 1, 90 degree. Okay, so here is dl cross with the unit vector r. So the direction of my current flow is positive z directions. Okay, and cross with my R. Okay, so my R is a little bit complicated. Okay, so you have to write term x plus 6 over square root 45 y. Right? Okay, so I will focus the first part. Okay, cos 0 minus cos 90, okay, is equals to 1. Okay, so it's 3 over 4 pi square root 45. Okay, square root 45 is, okay, I can bring in the square root 45 to make it become 45. Okay, so it is 5.31 milli, yeah. Okay, so now over here, okay, I have -3. Okay, so these I already bringing in here to get this value. Okay, so I have -3. So zx you get y. Right, zx you get y. Okay, so here is -y. Okay, and then zy you get -x. Okay, right, so you can multiply inside 3, so it's -0.016y. Okay, and minus 0.032x. Okay, so ampere per meter. Okay, the last step is to add them together. Okay, so the H total. Okay, let's see. Just now we have, okay, they are in different direction. So I will arrange accordingly. 0.032x minus 0.016y. Okay, and then minus 0.0711 sec. Okay, ampere per meter. So this is the answer, the magnetic field at the observation point P. Alright, now let's look at question C. So an infinitely long coaxial cable. Okay, so this is a coaxial cable. You can look at this figure Q2A. Okay, so this coaxial cable has a hollow inner conductor of radius A. Okay, radius A. Okay, and a cladding of radius B is made of a magnetic material of permittivity mu. Okay, and the inner conductor carry a total supply current I. Okay, so and the outer conductor carry a total return current I. Okay, so both are distributed uniformly around the respective cylindrical surface in the direction indicated in the same figure. Okay, so here I want to highlight to you that for the inner conductor, it is this one. Okay, inside is empty. Inside is empty. The current is just flowing on the surface. Okay, and this is the outer. Okay, outer conductor. Okay, so current going out here. Okay, you can see, and flow back here, outer. Okay, so this is how the current flow, okay, in the coaxial cable. Okay, this is how the cable works. Current is always flowing in the inner conductor and then return on the outer conductor. So in this case, you have to sketch the amperium path. Okay, amperium path in the region. So these are the region 1, 2, 3, and 4. So we are going to sketch 4 amperium path in these different regions. Okay, so here let's draw the big view of this coaxial transmission line. So you have an inner, right? This is your inner. Okay, and then you have outer, right? Outer. okay, and in between inner and outer, yes, you have dielectric, right? Two types of dielectric. Okay, so over here, according to the label, it is A, okay, A, and over here is B, okay, and C is over here, C. Okay, so I highlight again, this is the inner conductor, and over here is the outer conductor, okay. Okay, so I'm drawing the top view, the top view. Now we have to draw ampere path, okay, when the rho is less than the A, rho less than the A. Okay, rho is the distance, okay, that is smaller than A. Okay, so smaller than A, we could see that this is inside here. Okay, so you need to draw ampere path inside, okay, the regions, okay, that is distance is smaller than A. Okay, so this is smaller than A. And after that, we have to draw the ampere path in between A and B. Okay, you can see in between A and B, so you have ampere path. Okay, so this is your second ampere path. Alright, and then we have B and C. Okay, B and C. Okay, so you draw B and C ampere path. And lastly, you have rho greater than C. Okay, that is outside of the coaxial transmission line. Okay, so all these, okay, they are the ampere path. So you can label, okay, you can label for this one, it means for this, okay, and for the region in between this one, okay, A and B, so you can label it, okay, and for this one is in between C and also B, okay, can label it, and last one is to rho greater than C, is this one. Okay, so you have a total of 4 ampere path. Okay, so after that, okay, we have to calculate, okay, the magnetic field intensity. Instead of calculate, actually they want you to derive, okay, they want you to derive the equations of magnetic field in the regions that is between B and C. So which one? B and C is this one. Okay, this is one. Okay, so to come up with the equations of the magnetic field in coaxial line in this region, we have to apply the Ampere's law. Okay, so Ampere's law says that if we integrate, okay, the magnetic field, okay, in a closed loop, will be equal to the current that is enclosed by the ampere path. Okay, so look at the green color ampere path, okay, that you have drawn just now. Okay, so I highlight, which is this one. Okay, so this is the ampere path that you have drawn just now in between region B and C. Okay, so for B and C in this region, okay, your ampere path is only enclosing one current element, okay, that is your inner conductor. Okay, so here we will put I, and for the H, okay, H magnetic field, it will be in the phi directions, and you dot product, okay, you dot product with the R d phi, okay, R d phi, and in the phi directions. Okay, so this one is when we apply cylindrical coordinate system. So this is 2 pi. Okay, and dot product will give you 1. Right, so you have H, R, and 2 pi equals to the I, okay, of the inner conductor. So your H is equals to I over 2 pi R. Okay, so you can specify the directions here. Okay, so this is the magnetic field derivations using the Ampere's law. Okay, so this is the answer.